So, welcome to lecture on stability and steady state error. So, in this lecture we will discuss about stability. So, we know that there are three requirements for design of a control system, that is transient response, stability and steady state errors. So, these are the design objectives when we must satisfy these three according to our requirement when we are going to design a control system or a change a control system, existing control system. So, we discussed transient response already in the previous week's lecture, and now we will discuss the stability. So, first we define what is stability. So, the response of a system depends on the transfer function of the system and input of the system. So, we discussed that the input of the system, input that applies on the system governs the form of the forced response, and the second part, that is the natural response, is governed by the transfer function or by the system itself. So, the total response of a system is equal to Ct natural plus Ct forced. So, here this natural response that is due to the system's internal characteristic, and this is due to the input condition. So, when the stability can be defined based on the natural response, when the natural response of the system approaches 0 when the time approaches infinity. So, this C natural that should approach to 0 with the time, then we can say that the system is stable. So, for example, if we take one example here, this is time, this is Ct. Let us say there is this natural response of a second order system. This is the natural response of the second order system, and this response should approach to 0 with the time. For the undamped second order system, it is exponentially decaying amplitude. So, it should approach to 0 with time, then it is called stable system. And if this grows, so if this response grows, so we have, let's we start from here, and it is growing with time. So, it is growing. So, this is called unstable system, and this is stable. So, this is, and there is one more term that is called marginally stable. So, marginally stable system, when the response neither grows nor decays, but it oscillates. So, if this is oscillating like this with constant amplitude, so this is called marginally stable. So based on the natural response, we can define the stability and instability of a linear time invariant system. Now based on the total response, so total response is this is natural response, this is total response. So when we give some input to the system, some bounded input, so if we give some bounded input, it should give some bounded output, then the system is stable. When we are giving some bounded input and it is giving some unbounded output, then the system is unstable. So when we see the total response of a system, so when the transient part of the response grows without bound, and therefore it doesn't approach to steady state value. So because we know that we saw the elevator and we saw that the elevator response is approaching so to the input value, steady state value. But suppose it is not approaching to the steady state value, but it is something some other value, something some absurd value that is not approaching to some steady state value, unbound value. So this transient part is growing without bound, then we call it as unstable system. Now these are from the responses. We have discussed these definitions based on the responses of the system, one from with the natural response, other with the total response. Now we know that we have already linked the response with the poles and zeros of the system. So transient response we have already linked to the poles, with the poles the location of the poles. So we can also define the stability with the location of the poles of the system. So here we can see here that stable systems have closed loop transfer functions with poles only in the left half plane. So here now we discuss based on the poles. So we know that if we have some transfer function so this is a transfer function, and we can find the closed loop transfer function because this is the forward transfer function, this is feedback. We have to find the equivalent transfer function of this system, and this we can find, we can write Cs equal to Es into Gs, Cs equal to Es into Gs, and Es equal to Rs. So this is plus, this is minus, Rs minus Hs into Cs. So we can replace this Es with Cs by Gs. So here we can write Cs by Gs equal to Rs minus Hs Cs. So we want to find Cs by Rs. So we want a equivalent transfer function GES where there is input Rs and output Cs. So here we can write so Rs equal to Cs 1 by Gs plus Hs. This is equal to Cs 1 plus Hs Gs by Gs, and so Rs by Cs equal to GES. So here GES, so here GES equal to Cs by Rs. So output transfer function by input. So Cs by Rs is equal to Gs upon 1 plus Gs Hs. So this is called the closed loop transfer function. Or equivalent transfer function of this system. So this is an equivalent closed loop transfer function. And so when we base the definition of stability with the location of poles, we should consider for this system, we should consider the poles obtained from GES, because so when we say 1 plus Gs Hs equal to 0, and the poles that we get from this, so S, so those poles must be in the left half plane of the complex plane. So here if we have this plane, S plane, that is sigma j omega, that is S plane. So these poles must be left half. So this is left half plane and this is right half. So all the poles must be in the left half side. Then only, and no any pole to the right half side, then only the system is stable. And if any single pole is in the right half plane, then the system is unstable. However, what happens when the pole is here on the j omega axis or imaginary axis? So if we have n number of poles, because these poles will be in pair, so if we have this is omega 0, j omega 0, this is j omega 0 with minus sign, and we have on the imaginary axis these poles, so the response will be t k minus 1 cos omega 0 t minus phi. So if k equal to 1, this is 1, because k equal to 1, this is t power 0, that is 1. So we will have a harmonic response, something like this. However, if we have more poles on this j omega axis with multiplicity more than 1, so the pair of poles, if there is one pair of pole, then this is an oscillatory motion or oscillatory response. But if we have k greater than 1 more poles pair on the same axis, then we will have k equal to 2, then this will be t times cos omega 0 t. And so this response, when t will increase, this will increase, and again the system will be unstable in this case. Therefore, not more than, if there is one pole here, one pole pair, then the system is marginally stable. However, if there are more poles with multiplicity more than 1, greater than 1, then this system will be unstable here. So we can see that we can define this stability in three parameters. One is the natural response, second is the total response, and third is the location of poles. So with the natural response, if the natural response grows with time, then the system is unstable. If it decays to 0 with time, then the system is stable. If it oscillates with constant amplitude, then the system is marginally stable. With total response, the transients must lead to the steady state value. Transients must decay with time and lead to the steady state value, then only the system is stable. With the location of poles, all the poles must be left hand plane, left half plane, then only the system is stable. If there is any pole to the right half plane, then the system is unstable. So any pole here or here, this right half plane, the system is stable. So here it is stable and here it is unstable, and one pair of pole at the imaginary axis, that is marginally stable. But if the multiplicity is more than 1, more poles pair on this, then the system is unstable. So we saw that closed loop transfer function. From the closed loop transfer function, we must calculate the poles and not with the forward loop transfer function. So let's take one example. If we have this system, so this is Rs equal to 1 by S, and this system is 3 by S, S plus 1 and S plus 2, and this is Cs. So this system is, we can find the closed loop transfer function of this system. Let's call it Ts. So closed loop transfer function of this system, and then we can find the poles of this system. So when we find the poles, we will see that on this axis the poles lie to the left half plane, and this is minus 2.672 and this is 0.164, and this is J 1.047, and this is minus J 1.047, and we can see the response of the system with time for the step input Ct. Let's say this is 1, the step input, and the response will go like this. So we can see that here the poles are to the left half plane, all these, because there will be 3 poles. So these poles are to the left half plane, and the response is, the total response is going to the steady state value, that is 1, and system is stable. Now let's take another system. We have this system. So here we change this system, and we have here 7, put 7 here. So let's make another system here. So we have 7 by s, s plus 1, s plus 2, and we are interested in this Rs equal to 1 by s plus minus, and this is Cs. So for this system, if we calculate the poles Ts, here we should see that Hs is 1, because here is no Hs, means this is unitary feedback system. So Hs is 1. So this we can calculate Gs by 1 plus Gs. And so here sigma and j omega. Now if we plot the poles, here we have 2 poles, complex poles here. Point 0.0434 with plus side, the right side, and one pole is here minus 3.087, and this is J 1.505, and this is minus 1.505. So we can see that these complex poles, there are 2 poles to the right hand side, or right half plane. So therefore we could expect that the system should be unstable. So this is time, this is Ct, and this is 1, and we will see that the response will grow like this. So the response is growing, and so we can see from the response, when the transients parts is growing and not approaching to the steady state value, or the poles are to the right half plane, the system is unstable. Now if we take one more example. Suppose we have another system so s plus 4, s plus 6, s plus 8, s plus 10, so this is Rs, here is Es, this is Gs, and Hs is 1 if we compare to this. So we have to first convert, if we want to check whether the system is stable or not, we should calculate the poles. So we should convert this system into an equivalent system, and we can call that closed loop transfer function Ts. So this should be a system like this. Here is Cs, Rs, and when we calculate this, we will find tan s plus 2 upon s power 5 plus 28 s power 4 plus 284 s cube plus 1232 s square plus 1930 s plus 20. So this is Ts. So we can see that to find, we have to calculate the s, and then we have to see whether it is located on the sigma j omega axis, that is S plane. We have to locate it, and then we can tell whether the system is stable or not. So we have to need to solve this polynomial. Okay, this denominator expression we have to solve and find the values of the poles. One thing is clear, that we to get the information of the stability, we don't need the exact position of the poles or exact value of the location of the poles, but we only need to know that whether the poles are to the left half plane or in the right half plane or on the j omega axis. So only this information is sufficient to know the stability of the system, and only this information is sufficient for the design of the system. Once we are doing the analysis, then we may need to know the more details, but in the design stage we only need whether the system that I am designing is stable or not, and for this I only need how many poles are to the right side, or how many poles are to the left side, or how many poles are on the j omega axis. Therefore, we can avoid to calculate the values of the poles, but there are some methods that we can use to find that how many poles are to the left side or right side or on the imaginary axis, and with that information we can tell about the system's stability, and that we call is Raud-Hurwitz criterion for stability, and that we will discuss in the next lecture. So therefore I stop here, and let's see you in the next lecture.